Okay, so now we have all the pieces of our puzzle. The question, of course, is how are we going to find those weights W and those biases B that will get our classifier to do what we want it to do. That is, have a low distance for the correct class, but have a high distance for the incorrect class. One thing you can do is measure that distance averaged over the entire training set for all the inputs and all the labels that you have available. That's called the training loss. This loss, which is the average cross entropy over your entire training set, is one humongous function. Every example in your training set gets multiplied by this one big matrix W, and then they get all added up in one big sum. We want all the distances to be small, which would mean we're doing a good job at classifying every example in the training data. So we want the loss to be small. The loss is a function of the weights and the biases. So we're simply going to try and minimize that function. Imagine that the loss is a function of two weights, weight 1 and weight 2, just for the sake of argument. It's going to be a function which will be large in some areas and small in others. We're going to try to find the weights which cause this loss to be the smallest. We've just turned the machine learning problem into one of numerical optimization. And there's lots of ways to solve a numerical optimization problem. The simplest way is one you've probably encountered before, gradient descent. Take the derivative of your loss with respect to your parameters and follow that derivative by taking a step backwards. Then repeat until you get to the bottom. Gradient descent is relatively simple, especially when you have powerful numerical tools that compute the derivatives for you. Remember, I'm showing you the derivative for a function of just two parameters here. But for a typical problem, it could be a function of thousands, millions, or even billions of parameters.